Okay, so today we're going to talk about partial fractions, which is very useful in the field of calculus, as well as just useful in being able to see different things about rational functions that may not be as obvious when they are written in their normal, non-broken up form, if you will. So I'm going to go ahead and start with the problem here. X plus 8 over x cubed minus x squared. And so the first thing I'm going to do here is I'm going to go ahead and factor the denominator. If you notice, most of these problems you don't actually need to worry about factoring the numerator. Actually, that's not helpful, and I'll explain later why not. So let's go ahead and factor this. So the bottom, there's a greatest common factor of x squared, so I'm left with x minus 1. Okay, and now I'm going to do the initial setup for the partial fractions. So I'm going to say, I'm just going to copy the problem down here. And this one has some pretty interesting features about it. So if you notice, the x squared is actually a linear term written twice. In other words, it's x times x. And we know that y equals x is just a linear term. So this actually gets something interesting, which is a repeated factor in the denominator, and I'll show you what that is. So the step here is for a linear factor, such as x, okay, I'm going to write just a constant in the numerator. And then because x is repeated, in other words, it's x squared, it's not just x, but it's x times x, I'm actually going to write b over x squared. Okay, the squared representing the repeated x value here. Okay, if it was x cubed, I would have a over x plus b over x squared plus c over x cubed. If it was x minus 1 quantity squared, a squared right there, I would have not only an a over x minus 1, but a b over x minus 1 quantity squared. So what I'm going to do here is I'm going to then add the final linear term, which is x minus 1, because x minus 1 is a linear term, or a linear factor. And notice how each linear factor gets a constant, only a constant in its numerator. Okay. So so now I have the initial setup. So now what I'm going to do is I'm actually going to find out what is a, b, and c. So I'm going to multiply both sides by this denominator here to get rid of all of these denominators. So let's go ahead and do that. So I'm going to multiply by x squared times x minus 1. Okay, over here, these will obviously cancel. So I'm just left with x plus 8. That should always be the case. You're just left with the numerator on the left side. Here I have, let me write I'm multiplying by over here. Here I have an x, so one of these x's will go away, and I'll be left with an x and an x minus 1. So I'm going to write a x minus 1. The next one, the x squared, cancel the x squared, so I'm left with x minus 1. So I'm going to write plus b times x minus 1. And finally, the c term, or the c part of the partial decomposition, has an x minus 1 in its denominator, so those cancel. I'm left with x squared as the term that I'm going to multiply by c. So I have plus c times x, let me make that a little nicer, c times x squared. Okay. So now the next part is just kind of the most tedious part of these problems. I'm going to just do some algebra here, distribute, treating a, b, and c as constants. Okay. So in other words, this guy here is being distributed to both of these, and so on. the last term, obviously there's nothing to distribute. Okay, and now I'm going to rearrange them. So notice the left side is not changing. And how I'm going to rearrange them is I'm going to put the squareds with the squareds, the x's with the x's, and the constants by themselves, which here is just negative b. Okay, and now comes the part where I'm going to factor out the variable x, or x squared, from each term. So if I take out an x squared, I'm left with a plus c times x squared. Here, if I take out an x, I'm left with b minus a times x, and then I just have the minus b at the end. So I'm going to do my best to show you how to compare the coefficients of the two sides so that you can actually set up a system of equations and find a, b, and c. So a plus c here is the coefficient of x squared. Okay, if you notice, there is no x squared over here. Okay, so if you want, you could even write, if this is helpful to you, you can write 0 x squared plus all of that. Okay, otherwise you can just leave it alone and just realize that the coefficient of x squared is 0 because there is no x squared on the other side. Okay, so I'm going to say a plus c equals 0. Okay, now I'm going to look at the next coefficient, which is the coefficient of x, which is b minus a, and over here there is an x, and the coefficient of x right there is a 1, and since these are equal, right, I can actually set them equal to each other and set up the second part of the system, which is b minus a equals 1 for the reason I just explained. And lastly, I have the constant here, negative b, which should equal the constant here, which is 8. In other words, we have negative b equals 8. Okay, so right away you can see that b equals negative 8. So there's one of our constants. Okay, and I'm going to finish this problem on the next page, so we'll just draw an arrow here. So we have a plus c equals 0, b minus a equals 1. So let's write that here. A plus c equals 0. It's a little sloppy. B minus a equals 1. And we already know that b equals, according to the previous page, negative 8. So I can go up here and actually take my b value and put it in for that b value to find a. So here I'd have negative a, subtracting b from both sides, I'd have negative a equals 1 minus b, which means a is negative 1 plus b, dividing both sides by the negative 1. But we know what b is. B is negative 8, which means a has to be negative 8 plus negative 1, which is negative 9. And then since I know a is negative 9, now I can take this guy and put it up to this a and find c. So according to this equation here, c is equal to 0 minus a. In other words, c is equal to negative a. But if a is negative 9, then c must be the negative of negative 9, which is 9. Okay. And so altogether, if we go back to my original page, and I look here, I have a over x. Okay, so I'm going to write my final answer here. So a over x, where a is negative 9, plus b over x squared, where b is negative 8. And then finally, c over x minus 1, where c is 9. And so this would be the final, what's called partial decomposition of the original rational function, which was up here. So in other words, what I've done is I've taken this rational function, and I've split it up into 3 different parts, which actually can reveal quite a bit about the graphs of the original function, and can be useful in just determining how the graph is going to behave at different parts based on whatever interval you're looking at for the function. Also remember that, just some vocabulary here, each of these is called a partial fraction, okay? And altogether, it is the partial decomposition of the original function. So that was an example with linear factors. In other words, I had this x that was repeated, so that was kind of a special case, which is a linear factor, and then x minus 1, which is also linear, okay, matching the y equals mx plus b form of a linear equation. So let's look at one that may have a quadratic case. So for example, we'll call this number 2, negative 5x plus 8 over x cubed minus x squared plus 9x. Okay, so if you notice a few things about this, there's a cubic in the denominator. Right away, my first step is I'm going to factor the denominator by taking out an x, which is in common for each term. Okay, and actually, if you look at this and think about it for a little bit, if you try to factor this any further, there actually are no factors of 9 that add to negative 1. So this is a irreducible quadratic. So this is going to lead to a slightly different setup. So I'm just going to copy the problem down here, and we're going to get the basic setup here. So I have one linear term, which is x. In this case, it's not repeated. So I'm going to get a constant for that numerator because it's linear. Basically, it's one exponent or 1 power less than the denominator. This is linear, so this is constant. The next one is going to be quadratic, so the numerator will be linear. So what I'm going to do is I'm going to say plus bx plus c over the quadratic that is irreducible. So you can see here that I have a general linear equation right here, and I'm going to have the same goal. I want to find a, b, and c. So if you remember from the last problem, I multiply both sides by the denominator here, okay? So I'm going to multiply this by the denominator over here, and I don't have too much room on my page, so I'm just going to write the numerator down because we know that that's all I will be left with on that side. On this side, I'm also going to multiply by the denominator, okay? So just imagine that this is also written over here in this small space, okay? So I'm going to have a times x squared minus x plus 9, because the x here and here cancels. And then for the next one, all of this cancels, and I'm left with x times bx plus c. Okay, so make sure that you treat bx plus c as a unit or as a group. In other words, put them in parentheses. So I have this. Okay, so I'm going to have negative 5x plus 8. This becomes the tedious part, but just some algebra. So I'm just distributing, treating a, b, and c and x as constants. Okay, then I'm going to rearrange, putting the squares with the squares, the x's with the x's, and I notice there's one slight error up here. This x should be not an a. Okay. So if you figured that out as you were watching, that means you're paying attention, so that's good. So we have ax squared plus bx squared plus cx minus ax plus 9a, where 9a is the constant. So I'm going to go ahead and, before I compare the coefficients on both sides, factor out anything that I can. So I have this. And now comes the part where I can compare the coefficients. So I'll do the same thing here. I'll try and highlight the different parts. So the coefficient of x squared is a plus b. There is no x squared over here, which means a plus b is 0. So whatever a plus b are when you add them, whatever a and b are, whenever you add them together, you should get 0. Okay, you can do the same reasoning here. C minus a is the coefficient of x. The coefficient of x here is -5. So c minus a equals -5. Okay. And lastly, the constant, we have 9a equals 8, since those are the only constants. So 9a equals 8. So we're going to have some fractions here, but that's okay. Fractions are not a bad thing. So let's do the system on the next page. So we have a plus b equals 0. We have c minus a equals -5. And then 9a equals 8. Okay, so this one here will already reveal that a is 8 over 9. Okay, and what I'm going to do is I'm going to use that to find b and c. So this is a system of 3 equations with 3 variables, so I should be able to solve it. So I am going to do this first. Okay, you can actually find c or b in any order in this case. So if a is 8 over 9, this tells me that b is -a by subtracting a from both sides, where a is 8 over 9. So b is going to be -8 over 9. Okay, and then I can also take a and put it into this a. So I don't want to draw too many lines, but I'm going to take c minus a, where a is 8 over 9, okay, equals -5. So add 8 ninths to both sides. I have to do some fraction addition. Okay, so this can be written as a common denominator of 9. So if I make that over 9, 9 times 5 is -45. So -5 is equivalent to -45 over 9, which means c is -45 over 9 plus 8 over 9 is -37 over 9. Okay, so now I can finally write my final answer now that I know a, b, and c. And so if I go back to my original, I have a over x, where we found a to be, where's a? 8 over 9. So 8 over 9 over x. So we just have some fractions within fractions, in other words, complex fractions. That's okay. There's a few ways that you can reduce this if you want. I'm just going to leave it like this for now, but feel free to write it in a different way. Then I have bx plus c. Okay. Bx plus c, in other words, -37 over 9, all over this guy here, x squared minus x plus 9. x squared minus x plus 9. And so that is your final answer. Okay, so now you have an example that has not only linear factors, but a repeating linear factor, and an example with a quadratic that is irreducible, which leads to a form such as this.